Today we're going to look at the law of conservation of energy. So we're going to see how the different forms of energy can kind of slosh back and forth between each other, but the total amount of energy remains constant.
We'd usually state the law to the effect that energy cannot be created or destroyed, but only transformed or transferred from one form to another. Or we could say, maybe more simply, in a closed system, the energy has to be constant. It can do all kinds of transformations, but the energy as a whole, it's this kind of vague stuff, it's going to be constant. Now, the game that we're going to play is basically how do we keep score of where the energy is. We don't have a lot of equations for energy, but we've got a few, and we're going to be able to solve some simple problems using the few equations that we do have. So we've got this equation for work, and that's going to be very helpful to us. Normally, the force that we'll be talking about when we talk about work will be the force of friction. And of course, friction is going to act through some distance. And generally, when you have friction, you generate heat. So the transformation of energy that occurs here is usually to heat energy. But whenever we have friction and we have distances involved, we should be able to keep score of how much energy is being transferred. A second area that we can keep track of our energy has to do with the height energy, the gravitational potential energy. The higher something is above the ground, the more gravitational potential energy it has, and we can keep track of that quite easily. Now, usually what we'll do is we'll kind of talk about an absolute gravitational potential energy, MGH, but it's really the change in gravitational potential energy that's important. And we've also talked about kinetic energy, a half mv squared. And we've talked about elastic potential energy, a half kx squared. And just remember there that the x refers to how far the spring is stretched from its relaxed position. So let's suppose that in a relaxed state, the spring came to here, and when we pulled it out, it came out to here. Then this x, this here, would be our stretch distance, how far we're stretching it from that unstretched position. So what we can now do is begin to solve problems by keeping track of where the energy is. So here we've got three frictionless surfaces, and we're going to make them frictionless. So that's kind of critical. And let's say we've got a ball here, we've got a ball here, and we'll have another ball over here that's just going to, say, drop straight down. And we're going to make our distance that it drops down 5 meters. Now, if we think about the energy at the top, then at the top here, we've got some gravitational potential energy, MGH. And of course, it's the same for all three balls. And of course, it's quite easy to calculate how much gravitational potential energy it has up here, because it'll equal the mass. Let's use G equals 10. And the height here was at 5 meters. So we're going to have 50 m as the gravitational potential energy for all three balls. Now, if we think about the kinetic energy, well, we're releasing it from rest. So it's got zero kinetic energy in all three positions. Now, let's think about at the bottom. At the bottom, of course, in all three positions, the gravitational potential energy's got to be zero, because it's got no height. Now, there was no frictional force, so there's no other transformations of energy. The only transformation of energy is from that gravitational potential energy into kinetic energy. And so our kinetic energy at the bottom is going to be a half mv squared. Now, if we're going to have energy conserved, that means that that half mv squared has to equal mgh. And it doesn't just equal that in the first case. It equals that in this case, and even if the ball drops straight down. In all three cases, we should be able to write that 50 m has to equal 1/2 mv squared. GPE at the top has to equal KE at the bottom. Of course, the masses cancel out. We're expecting that because we know that all objects have the same acceleration in free fall regardless of their mass. And now we can multiply both sides by 2, and we'll get that v squared equals 100. And that means that in all three cases, the speed at the bottom is going to be 10 meters per second. So whether it drops straight down, comes down the ramp like that, or it comes down the ramp like that, speed at the bottom's the same. It doesn't mean the time to get there is the same, but the speed at the bottom is the same. In fact, there's lots of situations using this idea of conservation of energy that are mathematically the same. So we just saw a few of those. We saw, say, an object that's being dropped straight down, and we could ask, well, how fast will it be going at the bottom? And we saw that even if we had a slope, as long as it fell through the same distance, we'd get the same speed at the bottom here. And if we make our distance, say 5 meters, then the speed's going to be 10 meters per second. And the speed's going to be 10 meters per second in this case. Or we could even have the object do a loop-de-loop, like so. Because its change in gravitational potential energy is still the same in this case. And the speed here at the bottom is going to be, once again, 10 meters per second. We could even go in the other direction. How much speed do you need at the bottom in order to go up to the top? Well, you're going to have 10 meters per second of speed to make it up 5 meters. And once again, it's not going to matter what that looks like. As long as it's frictionless, you're going to have to give it a speed of 10 meters per second at the bottom. In all these cases, what you're doing is you're saying the gravitational potential energy at the top has to equal the kinetic energy at the bottom. That is, in all cases, you're saying 1/2 mv squared has got to equal mgh. And the m's will cancel out, and we'll get that v is equal to the square root of 2gh. And this will work in all situations where you have a direct transfer between kinetic energy and gravitational potential energy, such that there aren't any other forms of energy involved. So you can't have any energy going into friction, etc. So let's try an example where there is some friction. We've got an object. It's going to go down this ramp, but this time there is some friction. So what we're going to do is look at the energy that the object has at this position, and then look at the energies that the object has at this position over here. So if we start here, our gravitational potential energy will be m, that's the 2 kilograms. We'll take g equal to 10, and the height is the 20 meters. So if we multiply that out, we'll get 200 times 2, or 400 joules of gravitational potential energy at the top. Now, assuming it starts from rest, the kinetic energy will be 0. And at that point, friction has not had an opportunity to act. Let's consider the energies over here at this point. Our gravitational potential energy will be mgh, so that's 2 for the mass, 10 for g, and 5 for h. Multiply that together, you're going to get 100 joules of gravitational potential energy that are accounted for. Now, it also says that this object is moving with some speed. V equals 5 meters per second. So let's calculate its kinetic energy at that point. It's going to be 1/2 times 2 times the speed 5 all squared. So we're going to get 25 times 2, 50 divided by 2. That's 25 joules. In other words, we've accounted for 125 joules out of the original 400 joules that we had. And that means that we're missing some energy. And that's going to be 400 minus 100 minus 25, which is going to be 275 joules of missing energy. Well, if we think about that, the only other place the energy can go is into friction. And so the work done by friction is going to have to be 275 joules. Okay, with this IB question, very easy problem with energy conservation, much harder if you try other methods. What I'd like you to do is to pause the video, read over the question, try it out for yourself, and then come back for the answer. Now, to solve this problem, what we want to do, once again, is pick out these 2 points here and calculate the total energy at those 2 points. At this point here, we've got some gravitational potential energy, because the stone is raised up a distance capital H. So that gravitational energy will be equal to mg capital H. There's also some kinetic energy because the stone has some speed. that it's launched with, and that kinetic energy will be 1/2 mv squared. Now, if we consider at this point at the bottom, of course, there's no gravitational potential energy because it has no height. But it does have kinetic energy, and we'll give it a speed v primed so that the kinetic energy will be 1/2 mv primed all squared. Now, since this is a situation in which we don't consider friction, that is, air resistance is negligible, that means that we can say that the total energy here at the top has to equal this total energy here at the bottom. And we can equate those two to one another. That is, we can say that 1/2 mv primed all squared must be equal to mg capital H plus 1/2 mv squared. All the terms contain an m, so we can divide the m out. And then I'm going to multiply all the terms by 2, so I'll get that v prime squared equals 2g capital H plus v squared. And then I'll take the square root of both sides so that v primed will equal the square root of 2g capital H plus v squared. And then we look for that term, and here it is. Correct answer is D.
Okay, a question involving a bungee jumper. Pause the video, try the question, come back for the answer. So let's start with a little diagram. We know that we've got a platform which is, 50 meters above the surface of the water. The cord itself is unstretched for those first 10 meters. After that, that's where it begins to get stretched. So this here, where the person just hits the water, there'd be 40 meters of stretch to the cord. So now if we consider the total energy at the top and the total energy at the bottom, well, at the top, there's only gravitational potential energy. The cord is not stretched, and he's got zero velocity, so no kinetic energy. All of the energy is gravitational potential energy equal to mgh, and if you multiply 70 by 9.8 by 50, you'll get 34,300 joules. At the bottom, assuming there's no friction, the total energy has to be the same. Well, at the bottom, there's no kinetic energy because that's a turnaround point. They have no speed at the turnaround point. There's no gravitational potential energy because the height is zero there if we're measuring from above the water. So the only type of energy that you have is 1/2 kx squared, the energy stored in the spring. And that'll be 1/2 k times 40 squared because the cord is stretched by 40 meters. So in part A here, you can just say that the total energy is constant. So the energy at the top must equal the energy at the bottom. That is 34,300 must be equal to 1/2 k times 40 squared. And if you work that out, you should get a k value of 42.9 newtons per meter. And I'm extending that one extra significant digit so that we can use that in our subsequent calculations. But the answer should be 43 newtons per meter because our values were given to two significant digits, so our answer should be as well. Part B. So we're going to consider the case where they're 15 meters off the surface. There's still 10 meters of unstretched length. So 15 plus 10 makes 25. There must be 25 meters of stretching. So what we're going to do is use the total energy at the top, that 34,300. That has to be the same as the total energy 15 meters off the surface of the water. So we can say here, once again, total energy is constant. So we've got the 34,300 must equal the kinetic energy. 1/2 mass is 70 times the speed, which we're asked for, and that will be squared, plus the gravitational potential energy, which would be mgh, 70 times 9.8, and its height is going to be that 15 meters, plus the energy that's stored in the spring, 1/2. We worked out the spring constant to be 42.9. And we just said that the spring it's going to be extended by 25 meters from its unstretched length. So we'd have a 25 squared there. So we'll get 35 v squared equals 34,300 plus 10,290 plus 13,406. You should get that 35 v squared is equal to 10,604 when you subtract. So v will be equal to the square root of 303, which is equal to 17.4 meters per second, which you would round to 17 meters per second to two significant digits. In part C, we're asked for the highest speed attained. And in order to figure out at what height that occurs at, we have to consider the forces acting on the bungee jumper. So if I do a free body diagram of the bungee jumper, the weight is always the same, mg down. And then there's a force from the spring of k times x. Now, if mg is bigger than kx, of course you're going to speed up because there's a net downwards force. But if kx is bigger than mg, then it's going to slow down because there's a net upwards force. So the place where you get maximum speed will be when kx equals mg. So we can say that 42.9 times this x value, where you're going to get maximum speed, will be equal to 70 times 9.8. Work that out, and you get a stretch distance there of 16 meters. So we had a total distance from the platform to the water of 50 meters, 10 meters of unstretched length, and then x here is supposed to be 16 meters. 10 plus 16 would be 26. That means that we're 24 meters off the water. So we're going to do exactly the same thing that we did last time. We said that the total energy was 34,300. And that's equal to the sum of the kinetic energy, 1/2 m times v max squared in this case, plus mgh, 70 times 9.8, and the height is 24 meters, plus the elastic potential energy, 1/2, 42.9, times 16.0 squared. So we get 34,300 equals 35 Vmax squared plus 16,464 plus 5,491. So 35 Vmax squared is equal to 1, 2, 3, 4, 5. That's unusual. So we get that V will equal the square root of 353. And we get a final answer there, V equal to 18.8 meters per second, which should really be rounded to 19 meters per second. So let's summarize the big ideas from the video. we said that the total energy of a system will be equal to the sum of its kinetic energy plus any potential energies. And in particular, we would look at the gravitational potential energy and the elastic potential energy. Later on, we might look at electric potential energy, etc. But that total energy is constant if no frictional energy losses. So we can look at different points in time for our system, and we might get all kinds of transfers of energy, but that total amount would stay constant. If we have friction, then we can say that the total energy at the beginning, before any frictional losses, would be equal to the sum of the kinetic energy plus any of these potential energies, plus really the magnitude of the work done by friction, which would equal the frictional force times the distance. So in many cases, the frictional force will not be constant, but we could use an average force there. But all in all, if the total energy doesn't equal the sum of the kinetic energy and potential energies, then some of the energy was lost due to friction, and we can figure out how much at any point in the motion.
So please take the time to like videos, to make comments, to ask questions, become a subscriber, sign up for notifications, become a member or a Patreon. And that's all for today, folks. Thank you very much.